All right, so we just did the series circuit. Let's do a parallel. We'll do number 3 on the study guide. So we have a circuit, which I'll redraw here, starting in black, with a voltage source, full voltage of 12 volts. Imagine this to be a car battery or something. And now we are in parallel. So I have 3 resistors in parallel. And they are 1, R2, R3. And the first one is 8.2 kilo ohms. Next one is 6.8 kilo ohms. And the last one is 4.7 kilo ohms. Those are kilo ohms, so that's really 8,200 ohms, 6,800 ohms, and 4,700 ohms. So when you start calculating, make sure you're aware of that and notice that. So again, I'm solving for total resistance, total current, and then the current in each branch. Now we know the voltage across each branch because this is in parallel. Basically, this whole side here is connected to the same piece. This whole side might as well all be connected to the battery. So it's all at the same voltage across each one of these. Let's change. Well, actually, no. Let's do total voltage first. So if I wanted to do total voltage, I'll put voltages in blue. Oh, sorry, not the total voltage. The total current. No, let's do the current for each one first. It really doesn't matter what order you go in, but I feel like doing the currents in each one. So this would be I1, I2, I3 that we don't know. If I want current, I want voltage over resistance. If I want the current in the third branch, I want the voltage across the third branch and the resistance of the third branch. Now since they're in parallel, like we said, all the voltages are the same. So 12 volts, we have resistance of 4,700 ohms. So that gives me a pretty small current. 12 divided by 4,700 gives me 0.0025. Yeah, let's keep 2 significant figures here. 25 or about 2.5 milliamps. So when I write my answer down, I report it. I3 is 2.5 milliamps. If I use it to calculate other places, I may want to keep the 0.0025 amps. As long as you know what you're using and your units are consistent, you'll be all right. So I2, same process, same voltage. I'll just use R2 instead. So 12 volts. R2 was 6,800. If you stop a second and think, this is a larger resistance, which means we should have a smaller current if all goes well. So 12 divided by 6,800 is 0.0018. So that cannot be true, 1.8 milliamps for I2. And last but not least, I1, again, V over R1, 12 volts over R1 with 8,200 ohms. Gives me even larger resistance, so it's even smaller current, 8,200. 0.0015 or 1.5 milliamps. Alright, so now I have all those currents. Now Kirchhoff's current law basically said that, hey, all of the electrons that go into this thing have to come out. It's conservation of matter. The voltage law we saw before is conservation of energy. This is conservation of matter. So all the electrons that go in to here, as we have a much larger current coming through the battery, they all separate, some into here, some straight, some into here, some straight, and they all come back out and eventually come back into the battery. So the total current should be I1 plus I2 plus I3. So my total current is, I1 is 1.5 milliamps, plus 1.8 milliamps plus 2.5 milliamps. My total current is, grab the calculator, 1.5 plus 1.8 plus 2.5 is 5.8 milliamps. That's my total current. And last but not least, I wanted to know the effective total resistance of what we're dealing with here. So if I want total resistance in a different color, do something different, I rearrange Ohm's law. That's really voltage, total voltage divided by total current. Now we know total voltage and total current. So total voltage is 12 volts. The total, oops, that should be current up there. Just kidding. Voltage over current. So 12 volts over my total current that I just found was 5.8 milliamps. So you know what? Just to keep everything normal, I should keep everything in the original units. That'd be 12 volts over 0.0058 amps. Because a volt over an amp will give me an ohm. So let's see what that is. 12 divided by 0.0058 equals 2,069 ohms. That's my total resistance, or about, say, 2.1 kilo ohms. Now, if you notice, the total resistance is smaller than any one of the other resistances. As you add resistors in parallel, you're providing more options, more branches that the electrons could go through. It's like adding more lanes on a highway, more tolls as you go down the pike. It's easier to flow through when you have more options. Now there's another way you could have found the total resistance from the actual resistances themselves. If you didn't want to do the whole total current, total voltage thing, 1 over the total resistance equals 1 over R1 plus 1 over R2 plus 1 over R3. Right? So if we did that, we'd have to do 1 over 8200 plus 1 over 6800 plus 1 over 4700. Right? And to get the total resistance, we'd have to do 1 over all of that, or all of that to the negative first power. Because that would, just doing that by itself would give us 1 over the resistance. We need to inverse it again to get what we want. So 1 over 8200 gives me 0.000122 plus 1 over 6800 0.0001471 plus 1 over 4700 equals 0.0002128. Alright, all that is 1 over that, so alright, go back through and add it on my simple calculator here. 0.0001471 plus 0.00012 equals, I'm going to jump up here. Right now I have all of that's equal to, so right now 1 over the total resistance would be equal to 0.0004819. So if I take the reciprocal of both sides of that, I essentially get rid of this and take this to the negative first power, or 1 over that, I would get a total resistance of, flip it over, you might have a 1 over X button on your calculator, 2075 ohms, which through rounding and different things is pretty close to 2.1 kilo ohms. It will work either way you do it. Depending what you have, what you're starting with, what you're already finding, will determine kind of which way it's easier to do it. But that's a parallel circuit.